Jim Paulo， 来自意大利的 Jim Paulo， 他是 Python 核心开发代码开发成员之一他并且是2个重要类库的这个创建者和维护者，大家欢迎。
Sasa. 你好。Okay, so, ni hao. My name is Gianpaolo Rodola. I am from Italy. That's why I sound like Super Mario. I am mostly known for being the author of a PSUT library. It's a library for monitoring, and a FTP server library. So in this talk, I divided this talk in 2 main parts. The first part is how I sped up the file copy and file transfers for Python 3.8. And the second part is about PSUTO. So, Unix concepts. So what I'm going to say here is extremely oversimplified. I'm not a kernel developer, so take the following with a big grain of salt. So, system call. A system call is a way for a user space application to interact with the kernel. And most system calls are exposed in the OS module. System calls can be used for a variety of things, like interacting with the file system, or dealing with processes, or making the processes communicate, and so on. I think in recent Linux versions, there are around 400 system calls. So the kernel can be seen as a layer between the application and the hardware. So every time the application has to interact with the hardware, it never does that directly. It always does that via a system call. The operating system makes a clear distinction between user space and kernel space. You can see this distinction also in task managers like TOP. So for example, on a left, we have a pure Python application, which implements a loop. And since there are no system calls using this program, you can see that the counter which gets increased is the system counter. On the right, we have an application which generates a random string of a certain length. And because the algorithm to calculate the string is implemented at kernel level, the counter which gets increased is the system counter. File descriptors. So a file descriptor, it's a reference to something, which usually it's a file, but not necessarily. And file descriptors can be mixed together with system calls in order to get different results. So for instance, in this example, we use the standard output file descriptor with the write system call, and the effect we have is that we write something on screen, on the terminal. In this other example, we use a regular file descriptor, and by using read and write system calls, the effect that we have is that we interact with the disk. We read and write from and to the disk. In this last example, we use the standard output file descriptor, we mix it with IOCTL system call, and the effect we have is that we get the terminal size. So in summary, a system call is a gateway to the kernel. The kernel is a gateway to the hardware. The system calls cause a context switch, because that means that you go from user space to kernel space. And a kernel switch has a cost in terms of speed. And system calls and file descriptors can be mixed together. So, basic socket operations. So this is how we create a server in Python. We create an IPv4 TCP socket. We bind it on a certain address. We set a listen queue, and then we accept the connection. This is basically how any server application is implemented, more or less. So in Python 3.8, I included a utility function for the socket module called createServer, which does what we saw before, but in addition, it also lets you create a socket which is able to listen on both IPv4 and IPv6 connections. So with a single socket, you can handle both. Here we have the other part, the client side. It's basically the same thing. We create a TCP IPv4 TCP socket. We connect to the same address, and we can use a send and receive to send and receive data. Sending files. So this is how you can send a file in Python. After you accept the connection, you open a file for reading, you enter a while loop, and then you basically you send the file in chunks. You read a chunk of data, and you send that chunk of data. And when read returns an empty string, it means you reach the end of file. So two things are going on here. The first thing is that every time we call read and send all, we have a context switch because we go from user space to kernel space and back. So this has a cost. The second and most important thing is that we have a memory copy. So that means that when we call read, the kernel, we read from the disk. And in order to move the data to the application, to user space, it has to make a copy. And the same thing happens when we send that chunk via send all. The operating system, in order to move the data to kernel space, again, it has to make a copy. So in total, on each loop, we have 2 system calls, 4 context switches, and 2 memory copies. And this is expensive in terms of speed. So how can we avoid that? So the answer is by using zero-copy system calls. These are system calls that basically lets you do what we saw before, but avoid the copy operation. So the most famous one is a send file. This is very old. It's available in most Unix versions. This basically accepts 2 file descriptors, and it sends a file. Then we have copy file range. This is relatively new, and it's Linux only. It lets you copy a file, and in addition, it implements a server-side copy. That means that there is no data exchange between client and server. Then we have mmap. This basically lets you map a file into memory. This can be useful, for example, when you have a single file which is accessed by multiple processes. This can speed things up. Splice is more low level. It basically lets you connect 2 sockets. And this is usually used for implementing proxy applications. So when you use this, basically you have the flow of data all happening in kernel space by using 2 pipes. And then we have KTLS. This is a relatively new feature. I think it's Linux 4.13, if I'm not mistaken. This basically lets you use a send file, so avoid the zero copy, but in addition, it encrypts the data in kernel space. And this is how we make, we send a file by using send file. So send file accepts 2 file descriptors, the socket file descriptor and the regular file descriptor, a position, and the number of bytes to send on each loop. And when it returns 0, it means the whole file is sent and we're done, basically. So to compare the 2 approaches, by using send file, we have 1 system call instead of 2, 2 context switches instead of 4, and 0 memory copies, which is the most important thing. How much faster is send file? So I wrote this benchmark script. We can see 2 things here. The first thing is the transfer rate. The speed improvement is around 43%. Take these numbers with a grain of salt because benchmarking I/O is not easy. It's never stable. But more or less, this is the gain we have. And the second thing is the CPU. We use much less CPU, around 50%. So this is important because that means that with send file, you can build more scalable server. If we use less CPU cycles, that means that our server can serve more clients, basically. Another thing that we can notice is that because the transfer occurs in kernel time, the user time is much, much lower than the user time when using send. That's because the whole transfer takes place at kernel space. Okay, so send file has some limitations. It can be used with regular files only. And you cannot use it with SSL because, of course, you have to encrypt the data. That is why recently they introduced KTLS. And currently I'm experimenting with this. I'm trying to write a Python wrapper for KTLS, but it's very difficult. I still didn't get to it. So in Python 3.5, I included this socket.sendFile method. Basically, it does all. It takes care of all the low-level details, like taking care of the timeout, falling back on using all the read and write method, and so on. You can use it. You can use this starting from Python 3.5. And in Python 3.9, I have a patch, but I still have to finish, which adds support for transmit file on Windows. Transmit file is a system call, is a Windows API, which basically does the same thing as send file on Unix. So this is probably going to be included in Python 3.9. Copying files. So this is how you copy a file in Python. You import shutil module, you call copy file, you pass it a source path and a destination path, boom, the copy is done. So internally, this is how it's implemented. It's very similar to file sending. We open a source and a destination file, we enter a loop, we read from the source file and we write to the destination file. This is how the copy is done. And again, as like before, we have the similar drawback. We have 2 context switches and 1 memory copy per loop. Actually, sorry, 4 context switches and 2 memory copies. Again, we can use send file that starting from a certain Linux versions, which I forgot which one is it, you can use it also for copying files. So before you needed a socket and a file. Now you can also use it a file and a file. So that's how you can, basically you can use it for file copies. And the algorithm is pretty much the same. You pass it an offset, you keep track of the offset, you increase it on every loop, and this is how you make the copy. Again, we have some limitations. Send file can be used for regular files only. The destination files, it has to be open in write mode. The 2 files have to live on the same file system. If you attempt a copy on 2 different file systems, you will get an error. And I think, but I'm not sure, that you cannot use it with encrypted file systems. But I didn't try, so I'm not sure. So, other platforms. So, it turns out that the most used, the most famous platforms have something similar. On macOS, we have something called fcopyfile, and on Windows, we have something called Copyfile X. So these are exactly the same things. You know, they let you do a 0 copy. And all of these 3, they were included in Python 3.8. This is the ticket. How much faster is send file for copying files? So this is not easy to answer. It's not an easy answer. That's because shortly after doing this change, I quickly realized that benchmarking I/O is extremely difficult. That means that the timings that you get are very unstable. Okay, so one time you run it, you get 1 second. The second time you get like half a second and so on. So I used some tricks in order to try to minimize the differences. So first of all, I used the hot cache. That means that the source file is in the RAM. So I never access the disk. The second thing I did is that I set the highest priority for the process. That means CPU and I/O priority. That means that this process has higher priorities over the other processes. And in order to do that, I used psutil. And this is the results, more or less. This is the difference between Python 3.7 and Python 3.8. And on Windows and Mac OS, we get a nice 40 and 50%, which is not bad. So for Python 3.9, this is my next plan. I'm gonna use copy file range instead of send file. So copy file range, it works pretty much the same as send file, but in addition, it lets you do server-side copy. That means that there is no exchange of data between client and server. Basically, the client tells the server to make the copy, and when the copy is finished, the server will inform the client. And that works if you have network file systems like Samba. I have a working patch for this, but I still didn't, I still want to spend more time on it, writing tests and so on. So another thing I did in Python 3.8 is to speed up copy tree function. So copy tree basically lets you copy a directory tree, okay? You pass it a source directory and a destination directory. So the change I made is this. So in Python 3.7, copy tree used to use listdir function to get the file names, and for each file name, it used stat function to get the file metadata. Metadata means when you need to know whether something is a file or a directory or whatever. So in Python 3.8, I use something called the scandir. Scandir basically lets you get the file names and the file metadata in one shot. So by doing so, I reduced the number of stat system calls from 7 to 1. So it's a relatively simple change, but it's very effective. In here, I use the strace command. Strace is a Linux tool that basically lets you see the system calls used by a process. They are printed on screen. So with this, basically, I determined that with the new version of CopyTree, we have 38% less stat system calls. And this is the speed up. I wrote a benchmark script with 8,000 files split in 4 directories, and this is the speed up. So the interesting thing here, the difference between Windows and by using a normal hard disk and Windows network folder. So by using a network folder, we notice a bigger speed improvement because every time we call stat on a network folder, we are not accessing the disk, we are accessing the network. And of course, the network is usually lower than the disk. So that's why we see this difference between a regular directory and a network directory. Okay, PSUtil, completely different topic. PSUtil is a library I started writing 10 years ago, so it's a long time. It's used for monitoring system. And processes. So you can get stuff like CPU, disk information, network information, and so on. And the nice thing about it is that it provides a single API, I mean the same API for different platforms. So it's cross-platform. It works on most Unix version and on Windows. And soon I hope to add support also for Cygwin. So, PSUtil has around 70 APIs, so I'm not gonna go into all of that because it's too much. I'm just gonna quickly show you the most important APIs. So, CPU. This is how you can get CPU information about your system. You can get CPU times. You can use CPU percent to get the CPU percentage. You can use it in non-blocking and in blocking mode. And you can also get the CPU percentage divided by CPUs. If you have multiple CPUs, you can get this. Then we can get CPU count. This is also available in the standard library. What's not available in the standard library is the number of physical cores. Then you can get statistics like context switches, interrupts, and so on, and the frequency, the CPU frequency. Then we have memory. Virtual memory, basically, it's the RAM. The most important values here are total and available memory. And then we have the swap memory. Probably what's not clear here is S in and S out. Those represents the amount of bytes that there were swapped in and out from the swap partition. So that's something you have to keep in mind if you're monitoring memory. This is a script which lets you monitor memory. This is something I actually used in a previous company I worked for. In here, you can check the virtual memory to make sure that it never gets over a certain threshold. And you can check that the swap memory was never used. Because if at some point the swap memory was used, it means that we ran out of memory in the past at some point. Then we can query disks. We can get disk partitions. Disk usage. This is I contributed this back to Python 3.4 or something. So this is now in SHUtil module. Disk I/O counters. Basically, this lets you monitor disk I/O activity. This is a simple program that uses disk I/O counters API. Basically, you call disk I/O counters function before and after an interval. You calculate the difference between the two metrics, and this is how you get the disk activity. If you run this in a loop, you can see something like this. You can see the disk activity. In this example, I was copying a file. Network stuff. So we have net I/O counters. This is basically the same thing as disk I/O counters. It lets you monitor the network activity. So basically the most important thing here is bytes sent and bytes received. This is basically what your network interface does. Then we have net connections. This is similar to netstat command, on Unix. This basically lets you retrieve all the socket connections on the system. By socket connections, I mean IPv4, IPv6, and the Unix sockets. For each connection, you can get the family, the type, the local and remote address, the status of the connection, and the process that opened this connection. Net if addresses, this basically is like the ifconfig command on Unix. It lists the addresses associated with your network interface, if you need it. I never needed it. Sensors, this is, with this you can get the temperatures for different things, like the CPU, the motherboard, or whatever. Sensors fans, these are the fans inside the computer. You can get the speed, current speed. Battery, you can query the battery. You can get basically the charge left, amount of charge left, and whether the power is plugged. Load average, this is relatively new. I introduced this 6 months ago or something. So this represents the load of the system in the last 1, 5, and 15 minutes. So the numbers alone, they don't mean anything. They only make sense related to the number of CPUs installed on the system. So for example, 3.67 on a 10 CPU system, that means that the system load was 36% in the last 15 minutes. So this is useful when you want to know whether your system is overloaded or not. So anything, I will say anything above 70%, that means that your system is overloaded. If it reaches 100%, it probably means it's frozen. It's not responding. So the second most important thing you can do with psutil is querying processes. So you can get all the PIDs, all the process PIDs. These are the running PIDs on the system. Then you can instantiate a process class, and with the process class you can do a lot of things. I will not go into all of them because there are like 40 APIs, so I will go very quickly here. For each process you can get the process name, the command line, the path of the executable, username, status, and so on. You can know when the process was created, the creation time. You can get the parents, you can get the children. Children is useful when you want to terminate a process tree. And you can get the process environ. CPU, you can get the CPU times of the process. A relatively new thing here is the I/O wait counter. This is new. I introduced this because I needed to test an asynchronous I/O application. This is the time that the CPU spends waiting for disk I/O to complete, disk or network I/O. But when you have an asynchronous application, you want to know how much time you wait for the disk. So that's why I recently introduced this. And then you can get, of course, the CPU percent. CPU affinity, this is sort of exotic. Basically, you can tell the operating system to run this process on a certain number of CPUs only. You can tell the system, I don't know, I have 4 CPUs, you can tell the system, look, run this process on CPU 1 only. In certain cases, this can give a speed improvement depending on the CPU architecture. You can get CPU, the number of CPU the process is running on, and the threads used by the process. Then we have counters. I/O counters is basically the same thing as we saw before. It shows you basically the network and disk I/O activity of this process. Then we have a number of context switches. This was also useful. I used it for benchmarking the file copy, and a number of threads, a number of file descriptors. Then another important thing is this, the memory. You can get the memory maps. Basically gives you the shared libraries used by this process. Sometimes it can be useful. And then, of course, we have memory information. So memory information, the resident set size and virtual memory size, they are the most famous metrics when you deal with a process. But the interesting thing here is this one, USS. So USS it doesn't come from the kernel. This is calculated by psutil differently on each platform. And this represents the real memory usage of the process. It represents how much memory gets freed if this process is terminated right now. So it's very important. And in this example, this is a simple function which you can use to find the memory leaks. So let's say if you have a C extension which defines a C function, and you want to make sure that the C function doesn't have any memory leak, you can use this. You can call the C function many times and compare the memory consumption, USS and USS, before and after you call it 1,000 times. So if there is a big difference between the two memory metrics, that means that probably the C function has a memory leak. That probably means that you forgot to use free or something, you know? And at the same time, you can also check that the number of file descriptors is the same. So if the number of file descriptors increased after you call the function 1,000 times, that probably means that you forgot to call a close system call or something. So I needed this in psutil itself, because psutil is written half in Python and half in C. Okay, so I wanted to make sure that all the C code didn't have memory leaks. So in order to do that, I used psutil to test psutil, and I introduced this I added this to the unit tests. So every time unit tests are run, they test psutil APIs, and they also run something very similar to this to make sure that there are no memory leaks. So file descriptors, pretty simple. For each process, you can get the number of open files. This is similar to LSOF. There is a tool, a Unix tool called LSOF, which does something very similar. You can get the connections opened by the process, pretty similar as before. Signals, you can check whether if a process is running. You can suspend and resume the process. This may be useful, like if the process is consuming too much CPU, you want to temporarily suspend it. On Unix, this sends two different signals to the process. On Windows, this is implemented by pausing the process threads. So it's something completely different. Then you can kill the process. You can wait for the process to terminate. And priorities, this is also important. Nice, process nice is basically the process priority. By doing process nice -20, basically you can set the process to the highest priority. You need the root permissions to do this. And IO nice is the same thing, we saw it before. It's the IO priority. So let's say an example, this could be useful, like if you have an antivirus process, right? So the antivirus is the typical example of a process where you want a low priority. Because if the antivirus is scanning all your hard disks, right, it will like slow down your system. So you may want to set a low priority for something like that. And PR limit is something sort of exotic. So basically, you can decide to limit the process to, like, you can tell the process to open no more than a certain amount of files, or you can tell, I want this process to only use a certain amount of memory or of CPU and so on. So with this, you can do something like that. In this example, you tell the process to only use only open 5 files at most. And that's a soft hard limit. Basically, when you hit one of the two limits, you get a different Unix signal. But this is too low-level stuff. Let's forget about it. Finally, this is called Glances. This is a task manager, very similar to Top. I didn't write this, another guy did, but all of this can be seen as a graphical interface on top of psutil, because everything you see here is basically comes, with the exception of the Wi-Fi stuff, all the rest comes from psutil. So you can see the CPU stuff, memory stuff, the system load, all the information about the processes, the disks, the network, all this stuff comes from psutil. So yeah, it uses Curses library to model the graphical interface. This is it. 谢谢。
感谢 Paulo 的分享啊！大家有问题，现在还时间来得及，可以来提问啊。有要提问的吗 ？OK， 好 ，OK。Yeah, someone.
Yeah.
So, First of all, thank you very much for the sharing. And then, as you mentioned, you are the FTP developer. So very proudly to say, since last week, we start to use the FTP package.
Really?
Yep, exactly.
Nice.
So one interesting fact is that you mentioned that the send file,
Yes.
which in the 3.8 version of Python, which is released since, I think, recently.
Yeah. No, so send file in Python was added by me and another guy in Python 3.4 or 3.3. I forgot. So it's already available.
My question is that can we now already use the send file to reduce the cost when we are copying or let's say downloading or even make the change to the FTP files?
Yeah.
And second question is that is there any plan to say use these utilities for the future function when dealing with network files? Because the things is that nowadays we have a lot of data in, like, for example, we use Azure storage account to save our raw data.
Yeah.
And then when we do the analyzation, we have to always download it, unpack it, and then analyze it again, and then even upload it.
Yeah.
So it's extremely expensive. So is that a way, or let's say, is that already in the ticket system to say, okay, we'd like to have such utilities to make the change directly on the, for example, storage account?
It depends. So send file is already included into Python since Python 3.3 or 3.4, I don't remember. I also wrote a library for Python 2.7. So if you want to use it for Python 2.7, it's on PyPy. My FTP server uses send file. And Async.io, starting from Python 3.8, also uses send file. It has a send file method, which internally uses the send file system call. So the system call is exposed, it's used. So it's up to you whether you're using it or not. Like, it's up to the application. The biggest limitation of send file is the fact that you can only use it with clear text connections, you know, because basically it moves the data from one file descriptor to the other. So in order to encrypt it, you have to bring the data in user space, use SSL to encrypt the data, and then send it. But as I showed in the presentation, there is this new feature in Linux called the KTLS that also lets you do the encryption in kernel space. But that is very new. And this is what I'm working on right now. I want to expose this KTLS feature in Python so we can take advantage of send file also when using SSL. That's the biggest thing. Because send file is very effective because the speed improvement is around 50%. So it's a lot. But nowadays, everything is encrypted, right? You have SSL everywhere. You have HTTPS everywhere. So that's why send file so far remained kind of, unknown. But with KTLS, I hope that's going to change because, the speed improvement is a lot, You can save a lot of energy,
Cool. Thank you. And later, can we get the PPT download anywhere?
Sure. Yeah.
大家可以啊，到时候会公布一下地址，大家可以 download 这个。
Okay.
PDF 版本的。
Thank you very much.
Sure.
Okay. Thank you.
Thank you. 谢谢. By the way, I'm in Shenzhen for the next 3 months. So if somebody wants to meet, talk about Python or whatever, I'm gonna be here. Okay. 谢谢.
OK.